Outcome 1, Lesson 1, Charges. Part 1, Introduction to Charges. There are two kinds of charge, positive and negative. Positive charges are carried by protons in ordinary matter. Electrons are the subatomic particle that carry negative charge. Neutral is not a type of charge, even though when you think about matter, you think about protons, electrons, and neutrons. Neutral itself is not a type of charge. A neutron doesn't carry neutral, it just is neutral. Something is neutral if it either has no charge at all, like a neutron, or an equal, balanced distribution of positive and negative charges so that the positives and negatives cancel each other out. Atoms are made up of protons and electrons. The protons are found in the center of the atom. We call this the nucleus. The electrons are found outside the nucleus in what we call energy levels or orbits. So the protons are found in the nucleus, and the electrons are found in energy levels or orbits. This is important because it tells us that protons can't move. They are trapped in the nucleus. If you remove a proton from the nucleus, you change something fundamental about the atom itself. But electrons can be removed from their orbital shells or their energy levels without changing anything about the atom, just changing its charge. Any movement of charge in a solid is the result of movement of electrons. Here's an animation that helps you understand how electrons and protons are able to move when objects are charged. So you can see the sweater is neutrally charged. You can tell it's neutrally charged because it has an equal number of protons and electrons, and they're equally distributed. The balloon is also neutral, and you can tell this because it has no charge. Similarly with the wall, it has an equal amount of protons and neutrons, and they're evenly distributed. But if I rub the balloon on the sweater, the balloon is able to pick up some of the negative charges. You can see that the positive charges remain on the sweater because you can't move positives, they remain in the nucleus. However, the negative charges are able to be transferred to the balloon. Now the balloon is negatively charged and the sweater is positively charged. The law of charges say that negative charges are attracted to positive charges. So if I let go of the balloon, it will be attracted to the positive sweater. If I bring the balloon towards the wall, the negative charges in the wall are repelled from the negative charge of the balloon. Even though the wall is neutrally charged, it becomes attracted to the balloon, and the balloon sticks to it because the negatives move out of the way, leaving the positives behind where they remained. And the balloon that's negative is attracted to the positive section of the wall that remains. So from this we can see negative charges cannot move, and positive charges remain where they are. In the simulation, we reviewed the law of electrical charges. This law says that like charges repel, which means that if you bring a negative charge near another negative charge, they'll experience a repulsive force pushing them away from each other. Similarly, if you bring a positive charge near a positive charge, they will experience a repulsive force away from each other. The law of electrical charges also tells us that unlike charges attract. If you have an overall positively charged object and an overall negatively charged object and you bring them near each other, they will experience an attractive force pulling them towards each other. Although neutral conductors are attracted to charged objects, neutral is not a type of charge. You could see in the simulation that the wall became attracted to the balloon because the electrons moved out of the way leaving positives behind. The wall remained neutral, but the charge distribution, the location of the negative charges, changed. For that reason, sometimes we'll write neutral is attracted to charged objects like positives and negatives. Electrons in a neutral conductor redistribute to make it attracted to these charged objects. So, if you have a charged conductor that contains positive and negative charges, the positives stay where they are, but if you bring a negatively charged object near it, the negatives run away because they're repelled from that negatively charged object, and it leaves a positive side of the sphere. So we have an overall positive end and negative end to our neutral object. It's still neutral because it still has this equal number of positive and negative charges, but now the positive side can be attracted to our negatively charged object. Similarly, if you have a spherical conductor, and you bring a positively charged object near it, the electrons in the conductor will be so attracted to the positively charged object that they'll all move to be near it. Think of the positively charged object like a rock star, and all the electrons flock to try to be close to it. Now we have an overall negative side to our neutral conductor and an overall positive side. The conductor becomes polarized, and as a result, the negative end becomes attracted to our positively charged object that we brought nearby. If a neutral conductor is left alone, not near charged objects, the positive and negative charges will be equally distributed throughout it so that it has no overall charge. Part 2, Conductors and Insulators. A conductor is any substance through which electrons can move freely. This is often considered to be metallic objects, but there are other kinds of conductors as well. It's just that metals are generally very good conductors. Insulators are substances through which electrons cannot move. These are things like rubbers and plastics often. What is grounding? Often in electricity you hear people talking about grounding a wire. In electrostatics, the word ground doesn't refer to the earth or the floor. Ground is any neutral object that is large enough to hold a substantial amount of additional electrons without noticeable change in charge. You, for example, are a source of grounding for electrical wires. Think about it like the ocean. If you put a drop of water in the ocean, you aren't even going to notice that drop in amongst all the water that's in the ocean. It's just another little bit. Ground is a little bit like the ocean in that it's a huge amount of charges within it, so an additional 1 or 2 electrons doesn't make a difference. To ground a conductor, touch or connect it to this large neutral object. For example, if we have a negatively charged conductor, it's negative because it has more electrons than protons. If you touch it to a source of grounding, for example, a neutrally charged rod, the negatively charged electrons will drain out. If you have a positively charged conductor and you want to ground it, it's positively charged because it has more protons than electrons. If you want to ground it, you touch it again to a neutrally charged object. For example, here's a neutral rod. And electrons contained within that neutral rod are drained into the conductor as it's attracted to the positives within it. In other words, neutralizing, electrons flow into the conductor. In electrical diagrams, you'll often see the grounding symbol drawn like this. So we have a conductor, and if you want to, once it's grounded, it will become neutrally charged. The grounding symbol is drawn as 3 lines in a triangular shape attached to the conductor. Now, this grounding could either be a neutral rod connected to the floor or the ground source, or it could be simple as you touching the sphere, so you drain or add some electrons to the sphere from your hand. Insulators can't be grounded. If you try to ground an insulator, for example, a rubber ball, because electrons can't flow freely through it, the rubber ball will remain charged. So let's say that this rubber ball has a set of electrons somewhere on its surface. Because electrons can't flow freely, the insulator can't be grounded. The electrons get stuck. In clumps on the surface. As they're unable to flow through the insulator. Now, often you'll be asked to determine or describe the charge distribution on the surface of a conductor or an insulator when it's been charged. A conductor, when it's negatively charged, will have all the negative charges spread out evenly over the surface. This is because the electrons are repelled from each other. They don't want to be near each other. And because they're able to flow freely through the conductor, they spread out as much as they can to get as far away from their neighbors as possible. An insulator is a substance in which electrons can't flow freely. So if you add a charge to an insulator, it gets stuck. For example, when I rub a balloon in my hair, the electrons from my hair get added to the balloon where I rubbed it, and then they don't move. The electrons get stuck in clumps. And again, this is because an insulator isn't able to allow the electrons to spread out or move freely through it. An irregularly shaped conductor, for example a cube or any other shape that's not a sphere, will not have a perfectly even spread of charge as I drew in the diagram. Instead, the charges will tend to accumulate at the corners. So for example, in this shape here, which is sort of a scallop shell shape, you can see that there's a charge accumulation in the corner spot, a little bit more than the outside, even though it still is spread out. Part 3, charging by conduction and induction. Conduction is the transfer of charge by contact. This is a key part of the definition. It means in order for an object to conduct, it needs to actually be touching the object it's conducting electricity to. For example, if you want to charge a neutrally charged sphere by conduction, so here's our neutrally charged sphere. You can tell it's neutral because it has an equal amount of positive and negative charges spread out over its surface. You bring a negatively charged object near it, so it's touching. Here's our negatively charged rod. And it's brought near the neutral conductor. As a result, the negative charges from the rod are attracted to the less negative neutral conductor, and electrons will flow from the negative rod, spreading out into the neutral conductor. The neutral conductor becomes negatively charged because now it has more negatives than positives spread out along its surface. The neutral rod is less negative than, or the negative rod is less negative than it was before because some of its electrons have been transferred, but no protons have been added, so it's probably still a little bit negative. As a result of the conduction, the conductor becomes negative. If you want to charge a neutral conductor so that it's positively charged, here's again our neutral conductor. It has an equal amount of positives and negatives. You bring a positively charged object near enough to touch it. So I'm going to have a positively charged conductive rod brought near it to touch. Now, positives can't move. The positives from the rod can't flow into the neutral sphere. This is because positive charges are trapped within the nucleus. However, the negatives from the neutral conductor are so attracted to the positive rod that they'll spread out, flowing towards it, and some of them into it. As a result, the neutral conductor becomes positively charged because its positives remained, but it has fewer negatively charged charges in it than before. The positive rod probably becomes a little bit more or a little bit less positive because it's had a couple electrons added into it, but it probably stays a little bit positive. So you can see the neutral conductor becomes positive. This is really key. Charging by conduction tends to produce similarly charged objects. When you charge a neutral sphere using a negatively charged object, they both become negative. When you charge a neutral sphere using a positively charged object, they both become positive. Induction is another method that can be used to charge a sphere. Induction is the redistribution of charges in an object by bringing a charged object near but not touching. Conduction involves touching the two objects together. Induction involves two objects near each other but not touching. Charging by induction is a little bit more complicated. To charge a neutral sphere by induction, so here's our neutral sphere. We have to do it in stages. In the first stage, we bring the object we're going to use to charge it near it but not touching it. In this case, I'm going to bring a negatively charged rod near it but not touching it. In the second stage, you ground the conductor, leaving the negatively charged rod near it. As a result of the rod being near and the grounding, the electrons are able to move into the ground. So the electrons in the sphere don't want to be anywhere near the negatively charged rod, so that they flow into the grounding source and out of the sphere. In the third stage, you take away the ground and you take away the rod. So all that's left is the conductor and its remaining positive charges. When you charge this way, we started by trying to charge with a negative object, and we ended up with a positive conductor. Here's another example using the same stages. We have a neutral conductor, and we bring a positively charged rod nearby but not touching. In the second step, leaving the rod where it is, we ground the conductor so electrons can flow in and out of the ground source, in or out of the conductor. Now, remembering that protons can't move, so the positives remain where they are. Now, electrons want to be near the positive rod, and so much so that electrons from the ground flow into the conductor to be near it. Sort of like if the conductor was like a really awesome rock star and all the electrons in the ground hear that they're there and they rush in to try to be near it. They can't touch, but they can flow to the end of the sphere to be near it. Now there's more negatives than positives contained within the sphere, and as a result, when you remove the rod and you remove the ground, we end up with a negatively charged conductive sphere. Negatively charged because there's more negatives contained within it than positives. We started using a positively charged object, and we ended up with a negatively charged conductor. Charging by induction always results in oppositely charged objects. Part 4. Conservation of charge. I'll start this part by teaching you a little bit about charge. Charge is a measurable quantity in physics represented by the symbol Q and measured with the unit coulombs. So charge is represented by the symbol Q and measured with the unit capital C. I don't know why they chose Q for charge, probably because C was already taken by the speed of light, and Q isn't really the next best letter, but it's the one we're going to use. In nature, there are two particles that carry charge, the electron and the proton. The charge of the electron is negative 1.6 times 10 to the negative 19 coulombs. The electron has a mass of 9.11 times 10 to the negative 31 kilogram. The proton is positively charged, same charge as the electron, but opposite in charge. 1.6 times 10 to the minus 19 coulombs positive. However, the proton is much, much heavier than the electron. Well, the electron had a mass of 9.11 times 10 to the minus 31. The proton's mass is 1.67 times 10 to the negative 27 kilograms. You don't have to memorize these numbers. They're good to know, but they're found on your data table. So in the constant section of the data table, it tells you the elementary charge, E, is 1.6 times 10 to the minus 19. And in the particles section of your data sheet, the proton is given as positive 1e, and the electron is given as negative 1e, and next to them is their corresponding masses. In Physics 30, we'll often use the prefixed unit microcoulombs. Micro is a metric prefix that means 10 to the minus 6. So 1 microcoulomb is equal to 1 times 10 to the minus 6 coulombs. For example, how many electrons are in minus 7 microcoulombs? First, we need to convert the microcoulombs into coulombs. -7 microcoulombs times 1 times 10 to the -6 coulombs in 1 microcoulomb. The microcoulomb cancels out, leaving us with coulombs, so it's -7 times 10 to the -6 coulombs. We also know that the charge of the electron is 1.6 times 10 to the -19. So -7 times 10 to the -6 coulombs divided by 1.6 times 10 to the -19 coulombs per electron. This gives us 4.37 times 10 to the 13 electrons. Another example. How many microcoulombs are there in 45,000 electrons? First, we need to find out how many coulombs this is. So, there's 1.6 times 10 to the -19 coulombs per electron multiplied by 45,000 electrons gives us 7.2 times 10 to the -17 coulombs. Since electrons are negative, this is a negative charge. We want to convert this into microcoulombs. -7.2 times 10 to the -17 coulombs times 1 microcoulomb divided by 1 times 10 to the -6 coulombs. So coulomb cancels out, and we end up with -7.2 times 10 to the -9 microcoulombs. Conservation of charge. Similar to all the other conservation laws, conservation of charge tells us before an event and after an event, charge remains the same. Conservation laws always tell us something remains the same before and after. When two charged conductors touch and are separated, the total charge remains the same, and the total charge is split equally between them. Here's an example to help you understand this. If I take a 7 coulomb and a -3 coulomb charge and bring them together to touch, now since they're conductors, the charge can freely flow between the two objects. The total charge before was +7 plus -3 equals +4. Now afterwards, the total charge remains the same, but it's divided equally between them. So the two conductors after have equal charge equal to the same total that was there before. Here's another example. Two charged conductors are brought together to touch. Together, they form a total charge of -950 plus 200 is equal to -750 coulombs. We know after they're separated, the total charge must remain the same because of the law of conservation of charge. However, we know that this total charge is divided equally between them. So each conductor, after they're separated, has a charge of -375. Same total as before, but different distribution. It's distributed so it's split equally between them.